Hey everyone, we are from Team CS Trojans for the Obstacle Tower Challenge game. Obstacle Tower is a high fidelity, three dimensional game built by Unity Technologies using the ML Agents Toolkit and OpenAI Gym. An agent playing this game must solve both low level control and high level planning problems in tandem while learning from raw pixels and a sparse reward signal. The objective of the player is to cross as many floors of the tower as possible before the time runs out. With each increasing floor, the complexity of crossing it increases. The player will face challenges such as decreasing time, larger floor maps, locked doors for which it must find and acquire a key, and puzzles like Sokoban puzzle that must be solved. The game can be played in one of five themes, namely Ancient, Moorish, Industrial, Modern, and Future. The floor map is generated differently each time using procedural content generation. The action space is multi-discrete with 54 possible actions. The agent receives a reward only when it completes a task, such as crossing a floor, opening a door, solving a puzzle, etc. Our main aim in this project is to train an AI agent using state-of-the-art reinforcement learning techniques that can cross as many floors as possible. Upon performing literature survey, we understood the challenges related to the game, such as large branching factors, sparse rewards, large and complex state spaces, and the need to train for generalization. We knew that regular models like deep Q learning would not help us. To solve these challenges, we first tried an on-policy algorithm called the Asynchronous Advantage Actor Critique Model, which is developed by Google DeepMind. This model was built using TensorFlow and it combines the advantages of both policy gradients and value functions. It contains two components, the actor, which learns the policy, and the critique, which learns the value of a state and provides feedback to the actor to improve the policy. Since A3C is an on-policy algorithm, the agent learns while interacting with the environment. We trained this model for 10 million time steps using 4 workers, a batch size of 1024, a learning rate of 10 raised to the power minus 4, along with the Adam optimizer. As you can see in the demo, due to poor sample efficiency, the model is unable to learn a meaningful policy and either repeats the same action or spirals around the floor in a circle. This led us to realize that maybe the agent needs additional incentive to try different actions and explore novel states in the environment. We learned about the intrinsic curiosity module, which is a formulation to create an intrinsic reward signal. It was developed by Deepak Pathak and other researchers at UC Berkeley. The module comprises of two components, a forward model that aims to make the learned feature space more predictable, and an inverse model that helps learn a feature space that only encodes the features relevant for predicting the agent's actions. Making predictions on an efficient feature space provides the right amount of incentive to learn about a state. For implementation of the intrinsic curiosity module, we continue to use the actor critique method for the policy. The feature encoder is built using a CNN model. The forward and inverse models are multi-layer perceptrons. All these components were built using TensorFlow and Keras's model subclassing API. The models were trained for about 1 million time steps using the Adam optimizer. As we can see in the demo, the agent no longer gets stuck at walls and is able to cross the first floor, and sometimes even the second floor. It can also be noticed that when the agent arrives at a similar state again, it knows that there is no incentive to be there and moves away from it. This model too has poor sample efficiency, but we believe it shows a lot of potential for a game like the Obstacle Tower. In future, we hope to get better results by employing transfer learning to learn the feature space, performing hyperparameter tuning, and training for more time steps. Knowing that sample efficiency is a bottleneck, we researched about a new state-of-the-art model called proximal policy optimization. This model was originally developed by OpenAI. Although it is an on-policy algorithm, it is more sample efficient than its predecessors and provides smoother training. The key here is its loss function, which comprises a clipped surrogate objective function. We used the stable baselines library for PyTorch and trained the model using a CNN policy, a horizon length of 4096, a clip factor of 0.2, 4 epochs, and n steps of 6144. Using a reduced action space of 10 actions, training using the industrial theme, and performing extrinsic reward shaping also boosted the agent's performance. Upon training for 4 million time steps, we achieved the best result where our agent was able to acquire a mean reward of 6.8 and was able to cross 5 floors of the tower. As we can see in the demo, our agent is able to navigate through different rooms in the floor and find the door that leads to the next floor. It also notices and collects time orbs, which gives it additional time to explore the environment better. All the models implemented so far have taught us about the nuances of reinforcement learning and its applications on a challenging game like the obstacle tower. In future, we wish to try novel ideas such as behavioral cloning and hierarchical reinforcement learning to better solve the planning and generalization challenges. We would like to thank Professor Mike Zaida and the teaching team of CSCI 527 for their continued support during the course of the project. Thank you.